So what we'll do today is we'll go through the concept of thermodynamic cycles, which is the end of Chapter 2, and then we will start at the beginning of Chapter 3. We hit a little bit of the end of Chapter 3 when we talked about ideal gases, okay? So in very general terms, we talked about thermodynamic cycles as a set of processes that start and end at the same state, okay? So if, for example, with three paths, if the properties at state 3 are equal to the properties at state 1, then we say that it's undergone a thermodynamic cycle, okay? What we're going to do in this section is we're going to talk about 3 specific cycles that are given names, not just, leg 1 was constant pressure and leg 2 is constant volume, but 3 very specific cycles, okay? The first is a power cycle. And a power cycle develops energy transfer by work. So a power cycle, the takeaway is that work is done by the system. So for a power cycle in general, you get some kind of electricity out. This is in very broad terms, not specific to every power cycle. But you put some heat in, whether it's through hot gases or combustion, and you get work out. You undergo a cyclical process that repeats itself, and because the net result is a positive work, it's considered to be a power cycle, okay? The next one is a refrigeration cycle. So the goal of a power cycle is to produce work. The goal of a refrigeration cycle is to cool a space, okay? A power cycle uses heat in. A refrigeration cycle has an energy in by work. So I plug in the refrigerator. I cooled the space. That's a refrigeration cycle, okay? We're going to dissect these in detail in a minute. And then the last one is a heat pump cycle. Heat pump is actually the exact same cycle as a refrigeration cycle, but the goal is different. So the goal in refrigeration is to cool a cold body. The goal in a heat pump is to provide heat to a warm space. Okay. So both have energy input in the form of electricity, and both you're trying to capture some kind of heating, whether it's heat out or heat in. Heat pump cycle. Yes. So a heat pump outside your house, you use it to warm your house, right? So those are the 3 thermodynamic cycles that we're going to talk about, and I'll go through in detail and show you some schematics of those. It's maybe half and half, but there are a lot of pictures today, so that would be good. So power cycle, the purpose is to generate work. So you have a W cycle that you're trying to capture, okay? So the schematic for a power cycle, my system is some collection of gas or working fluid, whatever I'm going to define it as. It is in contact with both a cold body and a hot body, okay? So if you look at the schematic, Q out of the system to the cold body, Q into the system from the hot body, work out and is collected, okay? So W cycle, we're defining as the net energy transfer by work per cycle. Usually in the form of electricity. So a power plant that uses combustion to generate electricity is an example of a power cycle. What do you know, perhaps, about power plants? What are they usually situated near? Water. Why? Q out into a cold body. The cold body is water, so it discharges heat into a cold body. Combustion gases are the Q in. The work out is what you're generating, okay? So a power plant is an example of a power cycle. As we get further in the semester, we'll start really looking at power plants and identifying each process.
Is it the same power plant?
What's that?
Nuclear power plant?
Same concept.
It is the same concept?
Yeah, same
It's just-
concept.
I guess it
Every
just
the
uses a different
specifics
name.
are different.
Yeah.
Big picture concept is the same. Okay. So Qin is the heat transfer to the system per cycle from the hot body, drawn from hot products, hot gases, combustion, solar radiation, whatever you're using as your heat source comes from your hot body. Okay? Q out is the transfer of energy from the system to the cold body. And it's discharged to the surroundings. Okay? So what you have to get used to is as you see these figures, think about what is the cold body, what is the hot body, how can I compare that to what I know is actually occurring? Because as you start visualizing what's actually happening, it makes it easier to talk about the cycle itself. Okay? So power cycle, W cycle out, you have a Q in from the hot, a Q out to the cold. If I think of this in terms of a mechanics problem, and I do a sum of the forces, that's not correct, but I know you're used to thinking that way, I can generate an equation for W in terms of Q. Okay. So let me go back for a second. The equation W cycle is equal to Q in minus Q out. Okay. The next one, refrigeration cycle. Looks the same, it's not the same. So look and see what's different. What do you see that's different for the refrigeration cycle?
It's pulling the cold. Well, I guess it's not pulling the cold, pulling the lesser heat.
So Q in is coming from the cold. Work is going in instead of coming out. And Q out is going into the hot. So think about your refrigerator.
It's removing heat rather than adding.
It's removing heat from the refrigerator compartment, right? So it's keeping the cold body cold. The work is the plugging it in. So the work in is the electricity. The Q out of the cold body, this is your refrigerator, okay? This system are the coils that are in the back that contain the refrigerant and the compressor and the condenser and everything that's part of a cooling system. And this is when you stand behind your fridge and that hot air blows on you. That's the hot, okay? That's the Q out into the room, okay? So as you think about the cycle, think about, again, what exists, what you know, and how you can now think of it in terms of the schematic, okay? So W cycle is energy transfer by work to the system. Yes?
Another good example would be a window air conditioner unit or even a standalone air conditioner unit that you'd sit in a room.
Right.
It still needs to be vented outside.
Yes.
For hot air.
Right, yeah. And it pulls and cools the already cooler air. Yeah, good. So W cycle is in. Q in is the energy transfer to the system from the cold body. And in this case, the cold body is your freezer compartment or your fridge. And your Q out is the heat transfer out to the warm air, the room, whatever it is. The outside if you're looking at an air conditioner.
So the difference is it's by work to the system now as before it was work from the
Exactly, right. So what is W cycle, the sign of W cycle for a power cycle versus a refrigeration cycle? It's the opposite. Refrigeration will be negative because it's work done on the system. Power cycle, W will be positive because it's work done by the system.
And in terms of the basic science of just working in general before this would be negative technically, and the power cycle
Would be positive, yes.
So, you know how like late at night when
When you're in this guy's clothes.
when air conditioners seem like they don't really do anything, is it because it's colder outside?
Because the difference in temperature between the sink and the source are closer together. Yes, yeah. And we'll see that as well when we talk about engines and the temperature differences and efficiency and all of that. Yeah. Okay, so the other thing that's different, W cycle. Before was Q in minus Q out, now it's Q out minus Q in. Okay, so make sure you write that down. Got it? Okay, and the last cycle is a heat pump cycle. For a heat pump cycle, schematic is exactly the same as refrigeration. W in, Q in from the cold body, Q out to the hot body. What's different for a heat pump cycle is where you grab the thing you want. Okay? So for refrigeration, you wanted to cool this cold body and take advantage of that. For a heat pump, you want to take advantage of the top sink, the top the hot body. So this would be your room in the winter. This would be the heat pump that's outside in the cold. And you would be pulling, this would be the atmosphere, which is cold. And you're pulling the heat into the room and taking advantage of that. Okay? So focus on Q out, which is energy from the system. So the living space of a dwelling. Q in is the heat transfer of energy to the system from the atmosphere, the cold atmosphere.
So what's the difference between the refrigerated graph?
The cycle is exactly the same.
Okay.
It's just a matter of what you're capturing. Okay.
Okay, it's a different use of the...
Does anyone have a heat pump at their house? You can use a heat pump as an air conditioner, right? Depending on flipping a switch. Yeah, you do.
It doesn't work too well.
That I don't know. I don't know that I've ever heard of it used. Say that again.
It's for like the fall or the spring, but for like
When it's
summer,
really
like,
cold?
It's awful. Because it's meant for like temperamental areas where like the temperature difference isn't a lot.
Okay. So for a heat pump, W cycle, Q in minus Q out, just like the refrigeration cycle. So heat pump cycle, positive or negative work?
Negative.
Negative. Good. Okay. So purpose of heat pump is to pump heat to a warm body. Okay. So looking at the three of them together, just so you can see, you don't have to write all of this down, just so you can see the three of them lined up next to each other. So W is either work to or from the system per cycle, depending on which of the three you're looking at. Q in is heat transfer from the hot or cold.
So I'm guessing the equation we use is case specific, and the fact that if you like give us a test question that's a refrigeration cycle, we use the opposite.
Yes, yeah. So you have to know what cycle it is to be able to answer the questions for that cycle.
How would we be able to tell if it's refrigeration or then?
Well, there are two ways to look at this. One way is in the homework examples, you don't know what kind of cycle it is.
Right.
You're just solving first law charts for Q and W and all of that. You look at the W cycle, which is the total W. If it's positive, it's a power cycle. If it's negative, it's one of the two. You don't know which. Okay? Yes?
Can you say the conventions are working kind of based off of the second law of thermodynamics because Q out won't be the same as Q in, or what would be less than that?
We don't know the second law of thermodynamics yet. But yes, you can.
Okay.
Cold fusion. We don't know that yet either.
Are we going to do
We don't know that eventually the Earth is going to disappear and just keep getting hotter and hotter.
But he's taking it to get a grade, but he doesn't need it.
Oh, cool.
Okay, so now this is, to keep you, to wake you up with animations. I'll let you stare at that for a minute. Those are very small. So these are the three. This one, if I asked you which was which, right away you see that's work out, so you know that's a power cycle. Okay? The other two, depending on what your objective is, because the objective is determines which way you're viewing the cycle, can either be a refrigeration or heat pump cycle. Okay? Share? You want to share?
Nothing. No, he said that looks like his engine, and I said that's why Lance was a piece of poop.
Oh, wow. Okay. So the next stage is we understand what the cycle is. The next stage is you understand what the cycle is, power, refrigeration, heat pump. But how do we define it? How do we quantify it? And that is the concept of efficiency, okay? So we evaluate our cycle. How good is it based on a heat to work ratio? Okay. For a power cycle, we call that efficiency. So how efficient is your power cycle? For a refrigeration or heat pump cycle, we call it the coefficient of performance. So just conceptually, you can kind of imagine if I put, let's see, thinking of a power cycle. If I put a lot of heat in and I get very little work out, that's going to be less efficient than putting a lot of heat in and getting more work out. Okay? So we're looking at how much work do you get for the amount of heat in, or for the other cycles, how much work do you get, how much work do you need to put in for a given amount of heat? Either removed or added, okay? So there are a bunch of equations. I kind of summarize them in one table rather than deriving them. If you want the derivations, they're in the notes. So the summary of cycles in terms of work and efficiency. So for a power cycle, the efficiency, we call this term eta. It's Greek letter N. That's the efficiency of a power cycle, and it's equal to the work you get out divided by the heat you have to put in. Okay? Both are units of kilojoules, for example. So what's the unit on efficiency?
0.
It's, kilojoules per kilojoule. No, I'm kidding. It's not. It's unitless. Yeah.
Oh, we're allowed to use one.
Yeah, you're allowed to say unitless.
It's the first thing in thermo that doesn't have units.
So if I recall that W cycle is Q in minus Q out, and I rewrite the equation, I end up with the efficiency is 1 minus Q out over Q in. Yes?
Why isn't it Q in over Q out as the ratio? Why can't we say that's true?
Why can't you?
Yeah.
Because the
Because if Q in is always going to be smaller than Q out, and the ratio has to be less than 1. So why can't we say it's Q in over Q out?
Isn't that second equation? That's a law. I think I've seen, like Carrot's law or something. No,
I
wait,
don't know
that
what it
basis.
is.
Never mind.
I don't have an answer to your question right away. I have to look at the. You're saying conceptually rather than equation-wise,
Yeah.
like because these equations work out to that, and you're saying why can't you just conceptually? It relates to T in and T out,
Okay.
but I would have to noodle on that for a bit. So efficiency, 1 minus Q out over Q in. So in terms of problems and what problems you're given to solve, if you're given a work and a Q, you can use the first equation. If you're told what the heat in and heat out are, then you can solve for the second equation. If you're given an efficiency and some Q's, you can solve for work. There's all kinds of ways you can go with these equations. Okay? For a refrigeration cycle, we use beta as the coefficient of performance. And beta is Q in over work cycle. Work cycle is Q out minus Q in. So my beta can be greater than 1, as in the heat pump cycle, measurement of performance can also be greater than 1. Okay. And heat pump, we use gamma, Q out over work cycle. Plugging in Q out minus Q in for work cycle, I can get gamma either in terms of work or simply in terms of heat. Okay? Okay? So in terms of evaluating the performance, these are equations that you just have to know. Okay? To be able to solve for those. So efficiency of a power cycle will always be less than 1. Everyone ready? Efficiency will always be less than 1. Or less than 100%. Usually efficiency is reported as a percent, so 50% efficient. Okay? So what that means is only a portion of the energy added by heat can be obtained as work. You're never going to get all of your heat to be removed as work. The remainder Q out is discharged to the surroundings. Okay? So go ahead and solve this. You do have to read it, but then solve it.
And there's some sort of law pertaining to this. What is he talking about?
You'll eventually learn it.
It's not good enough. That's not good enough.
So how efficient is like a refrigerator?
So really it's just grabbing your power cycle equations. W cycle equals what? Q in minus Q out. Both of which are given. So, but you should always check to make sure. If you don't remember whether it's Q in minus Q out or Q out minus Q in, you know that a power cycle has to be positive work.
Yeah.
So just subtract the smaller one from the bigger one. Okay? So for a power cycle, Q in minus Q out gives 400 kilojoules, which is your work cycle. And then the efficiency you can do in one of two ways. You can either use the Q in the work in the equation, or you can use the Q in and Q out in your equation, both of which will result in the same answer. Okay. So W cycle over Q in is 400 kilojoules over 1,000 kilojoules, so 0.4 or 40% efficient. Okay. You could have also used 1 minus Q out over Q in, which would also give you the 40%.
So the Kelvin was just useless.
Yes, it was. Just make you question whether you're doing it right.
That's the worst.
How do you know what?
Q in minus Q out just because of the way it said it went through.
Yes.
Okay.
Yeah.
I get confused.
And again, if you draw
Saying it would show it.
everything going in as positive and everything coming out as negative, you would derive that equation. Okay? Okay, another one.
This one's in Celsius.
Does it matter, though, is the question.
No. Yeah. It is automatic.
So heat pump cycle, you know what you expect for your work. Discharge 900 kilojoules of heat, receive 600 kilojoules. Find the network input and the coefficient of performance. So again, another straightforward plug into the equations.
Can the coefficient be negative?
No.
If the work cycle is negative.
I say do an absolute value
Okay.
because it shouldn't be negative.
So my answers.
Is it okay if I start abbreviating coefficient of
COP, that's how we abbreviate it.
co? I put co for
No, COP, capital, COP.
Oh, it is still positive. Sorry.
It's a work input. 3, yeah. So W cycle is Q out minus Q in, which is 900 kilojoules minus 600. Okay.
So if we do ever come across
Absolute value, because it's all in the semantics, which is a lot of thermodynamics is in how you word it. So if it's the work input, that would be positive, right? Because you're giving, it's already asking you for what's going in, so you're defining in as positive. If you do a first law chart and do a cycle, you should get a value of negative, okay, which is understood as work in. So it should be positive, this is the bottom line.
Yeah, but this,
Because it's,
we don't have negative kilojoules because are we just to assume that it's negative work?
by saying work in, you're saying it's done on the system.
Okay, sorry.
Yeah, yeah. So it's the terminology of it. Yeah. Okay, and then gamma is Q out over work cycle, so 3.0. Note the coefficient of performance is a numerical value. Okay, so efficiency is usually reported as a percent. Coefficient of performance is reported as a number, not a percent. Okay.
They put that on refrigerators, coefficient.
They give a performance, but I don't think they give a coefficient. Pay attention to that. I'm not sure. 3. Yeah, that wouldn't impress people, would it?
So wait,
They give an energy.
what's the scale? Looks like good.
I can't even tell you what's good.
1.21 gigawatts.
Amazing.
3's amazing.
Yeah, if you hit 4,
1.21. Okay, so now I'm going to tax your brain a little bit harder.
Ooh,
Okay.
that's not nice.
So
there's less words. I'm finding
this is very much like your homework, though, so this should be helpful.
yeah, basically.
Less words.
So piston cylinder assembly, thermodynamic cycle, and you're given 3 processes and descriptors for all 3. Okay. So U is internal energy. Process 1 is a compression with U2 equal to U1. Okay. 2 to 3 is constant volume cooling, and you're given a P3 and a V3. And 3 to 1 is a constant pressure expansion, so P3 equals P1. And you're given the work as a positive 10.5 kilojoules for that path, for that process. Okay, so here's a good example of where you're not just given values for your property chart, you're given values for your first law chart as well. So when you start constructing the solution, put a property chart and a first law chart and fill in the knowns and then work from there. Okay. Internal energy. So you are also given that the net work is negative 8.3 kilojoules. Okay. KE and PE are constant. That becomes important because your delta E is now only an internal energy change. And you're asked to determine the volume at state 1, the Q and the W for process 1 to 2, and whether it can be a power cycle or a refrigeration cycle.
So if you're not given a governing equation, are you to expect that work equals PV and it's
For each process, you can tell me an equation. Okay? Like constant volume, your equation is V equals constant, V2 equals V3.
oh yeah, 'cause
Okay.
constant pressure heat.
Yeah. Yes. Or you could just do P equals constant, P3 equals P1.
Okay.
Yes.
There's an equation, I forget what exactly it is, but it has delta KE plus delta PE
Plus delta U
equals something.
Q minus W.
Q minus W. Now, for this KE and PE would just go away?
Those go to 0.
We don't need those?
Right.
All right.
Yeah. Now that equation is the first law, so make it more important in your head. I don't know what the equation is, but it involves, yeah. So first law, delta KE plus delta PE plus delta U equals Q minus W. You're told that KE and PE are constant, so just cross those out. It becomes delta U equals Q minus W. Okay? So I'm going to move on, but it's kind of repeating what we just saw. So there are your three processes. And you also know it's a cycle. Okay? So when you construct your first law and your property chart, I don't want to show you too much. I want you to fill it in yourself. So do a property chart that has state, P, V, and U in it. U is a property. So that needs to take its place in the property chart when it's relevant to the problem. W and Q are not properties. Those don't go in the top chart. Those only go in the first law chart. Okay? So before I put that up there, state, P, what units are P? Kilopascals. V and U in kilojoules. So that's your property chart, and then your first law chart. Remember, in your first law chart, it makes no sense to say state. You need to indicate the process. W. I don't really leave enough room, but for your first law chart, give an equation for each state, and the equations can be V equals constant, P equals constant.
Delta U?
Delta U, yeah. I am going to pull back to the previous slides that I skipped today. One of the things I introduced was the concept of constant volume specific heat, C sub V, if you didn't look at the notes. I suggest you go back and look at them. But basically what it said is that delta U is equal to CV delta T. And the reason I'm bringing that up is because if U is constant, that means T is constant. Okay? U depends on temperature. So the equation I want you to use here for process 1 to 2 is T equals a constant. Okay? So T1 equals T2. V equals a constant, P equals a constant. Okay. So what I want you to do is, based on the givens, fill in as much as you can of these two charts to start. The other thing in your first law chart when you're dealing with cycles, I don't really have enough room here, but add a lower line for the cycle. Okay. So the way you start is fill in what's given. So what do we know? What can we start filling in here?
We have the pressure at state 1 and 2 is 140 kilopascals, and the volume for state 2 and 3 are both 0.028.
Wait. This is 3 and 1, right?
Yeah,
Say that again, and what's next? Volume.
Volume is 0.028 cubic meters at state 2 and 3.
Okay. We don't know any of these at this point. The U's, right? What?
10.5?
What do we know that? That's not in your property chart, so
That's where
leave.
process 3.
That's all we have for this. So let's now go to our first law chart. What can we fill in? Gary, what'd you say? 3 to 1?
Yes,
Yeah, 3 to 1.
W. 10.5?
Yes, kilojoules.
Okay.
Cycle is negative 8.3.
Cycle is negative 8.3, so I can fill that in. That was given.
Okay.
Okay. What do I know about delta U from 1 to 2?
It's the same.
0, right? Because I'm given U1 equals U2. So delta U is 0. One more. I'm guiding you on this one. You might get.
So because process 2 to 3 is isovolumetric, you could say work equals 0.
Good. Everyone pick up on that?
Yeah.
2 to 3 is constant volume, so work equals 0. One more thing. For a cycle, the property change is 0. Okay? So the cycle delta U, because U is a property, is going to equal 0. Okay? So now this is where it gets fun, because this is like a puzzle, and you have to say, what do I know and what can I get? So I want you to start trying to dissect. Yes?
I have a question. If delta U for the one cycle is 0 and the overall for the cycle is 0, wouldn't that mean that the U for process, the delta U for processes 2, 3, and 3, 1 would be the same? Or
Opposite.
opposite?
Opposite.
Same
Yes, in
magnitude,
fact.
Same magnitude.
Yes. Yes. Okay, so that's one good thing to think about. What can I do here without taxing my brain too much? What can I get? What do I mean by cycle? What is this?
It repeats.
No, in terms of the chart, what does cycle, how numerically? It's the total. So Martin, you said it. What is it? Work from 1 to 2 I can get because I know everything else. Right? So go ahead and get a work 1 to 2.
That's the total.
Say it again. That was correct.
Negative 18.8.
Negative 18.8 kilojoules. Next.
And you also know that because delta U is 1 for processes 1 and 2, Q and W have to have the same thing.
Good. So since delta U is the same, or so U is the same, so delta U is 0, I know that delta U equals Q minus W. That's my first law. So Q has to equal W. So I've solved for W. Now I can fill in Q.
Okay, how did we make it negative 18.8?
These three
Right.
equal negative 8.3.
Right. Oh, okay.
You probably put something on the wrong side of the equation.
No.
Maybe.
Yeah, I don't know.
So
I was not thinking about that the right way.
So, well, I just gave you that one. Nobody contributed that one. This is 0. I know the W cycle, which means the Q cycle has to equal W cycle. Okay?
and it's the same thing for 1 and 2.
1 and 2.
Cos of 18.
No, but it's still negative. Because 0 is equal to Q minus W, so they're equal to each other. Okay? So, everyone good so far? I might actually have to do some work. Unintended. Actually, I don't even think it asked you for the rest, so we don't have to worry about that. What did it ask you for?
Volume.
Q and W for
Volume 1. Yeah, it's for
1 to
volume
2. Okay? So how would I get volume 1?
I use the work in process 3 to 1. And I solve for volume that way. By
Okay.
setting P
Oh, with the
as
integration,
constant
yep.
and just divide
Good.
by P.
Everyone hear that? To solve for the volume at 1, you know work 3 to 1,
And the pressure's constant.
and you know pressure is constant from 3 to 1. So W is equal to the integral of P dV. You can pull P out, and it's from 3 to 1, so your upper limit is 1 and your lower limit is 3, or vice versa. So you get that 10.5 kilojoules equals integral of P dV from V3 to V1, pulling P out. You can solve for V1 because it's the only unknown in that equation. Okay. 0.103 cubic meters. Okay. Nice thing about this is there are no conversions you have to do at all. Just plug in and the numbers you get are the numbers you get. That makes sense, Brandon?
Oh, yeah, kind of. Really hungry, tired.
Okay, so it asks for V1, which is 0.103. It asks for Q and W for process 1 to 2, which we solved for. And the last thing it asked is, can this be a power cycle or a refrigeration cycle? What can it be? How would I know?
Negative. It's be a heat pump.
Negative work, so it cannot be a positive cycle. Negative cycle work, but it could be a heat pump or a refrigeration cycle. Okay. So the reason it shows up negative here is because you're calculating a direct work value. When the equation or when the question is termed work input, that would be a positive because it's work in.
Work output is negative.
No. It's like if you called the work input, it's almost like when in statics, if a force is going down and you've defined down as positive, you would make that value positive, right?
Okay.
So this is kind of the same
we've
thing.
defined this as-
You've defined input as positive by asking the question that way, by saying, what's the work input?
So, okay.
If you
it's
told
the-
me the work input was negative, you would be telling me it's output. Okay,
Yeah, that makes sense.
all right. So it can be a refrigeration or a heat pump cycle. That is where we're going to end today.